All right, so in 8.3, we did what we call reciprocal functions, which are like the simple rational functions. These ones we're going to graph really any kind of rational function and talk about how the asymptotes work and different things like that. So a rational function in general is the form f of x equals a of x over b of x. So we no longer just have a number in the numerator. We could have a whole function in the numerator, whole function in the denominator, so it works like that. So the zero of a rational function, remember zero is the same thing as x-intercept. So if you're looking for where the graph crosses the x-intercept, it's a good thing to look for. Both zeros and intercepts and asymptotes are good things. They're kind of helpful to graph our rational function. So zeros would be when the numerator is equal to 0. And we've done that plenty of times. You kind of take your function, set it equal to 0, and that helps you to find your x-intercept. So that's how you find what we call the zeros. And then our vertical asymptotes is going to be whenever the denominator is equal to 0. And we did that with 8.3 as well. Whenever the denominator is equal to 0, you're going to have a vertical asymptote. And then dealing with horizontal asymptotes are a little bit more complicated. They've got these 3 different horizontal asymptote rules that we can follow, and it all depends on the degrees of the numerator and of the denominator. So here are 3 rules. Okay, so rule number 1, if the degree of the numerator, I'm going to write it as shorthand as I possibly can, if the degree of the numerator is greater than the degree of the denominator, in that case, that's something like this first one down here. You've got an x squared in the numerator, whereas you only have an x in the denominator. If that's the case, you have no horizontal asymptote, just like in that picture. Okay, so again, the way that looks is in this example down here, the degree of the numerator is 2, the degree of the denominator is 1, and if that's the case, there's no horizontal asymptote. Okay, so that's our first rule. Second rule is if the degree of, just a of x, if the degree of the numerator is less than the degree of the denominator, we always have a horizontal asymptote, and in this case, it would be a horizontal asymptote of 0. Okay, so if the degree, and that's supposed to be just an a of x, sorry, if the degree of the numerator is smaller than the degree of the denominator, horizontal asymptote is 0, so that goes with our middle picture here. The degree of the numerator is just 0 because there is no x term. The degree of the denominator is 2, and you see that right here, y equals 0 is what we call a horizontal asymptote. So that's our second rule. Third rule is if the degree of the numerator is exactly the same. And in this case, it's a little bit complicated. The horizontal asymptote is, we write this as y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay, sorry, I keep trying to do parentheses instead of a's. There we go. So the leading coefficient of the numerator divided by the leading coefficient of the denominator, and we've got that happening in our third picture here. Here the degree is 1, here the degree is 1, and so our horizontal asymptote is 2 over 1, which is 2, and so that's our horizontal asymptote there. Okay, so those horizontal asymptote rules are a little bit complicated. They might take some getting used to. We're going to write just some more details here on actually graphing these rational functions. So zeros versus vertical asymptotes. People have a tough time with these. One thing to keep in mind is the numerator versus the denominator. So the zeros are when the numerator is equal to 0. The vertical asymptotes occur when the denominator is equal to 0. So zeros are when the numerator equals 0. Vertical asymptotes are when the denominator is equal to 0. So do your best to keep those straight. Okay, so here's how we're actually going to graph these functions. So first thing, we talked about the zeros versus the vertical asymptotes. We're going to end up plotting zeros, vertical asymptotes, horizontal asymptotes. We're also going to plot the y-intercept if it's applicable, and that'll give us just kind of an extra point to go off of. So first step, we are going to find the zeros, and the zeros are also known as the x-intercepts. Those things are one and the same, and we do that by taking the numerator, a of x, and setting that equal to 0. And then we are also going to find the y-intercept. Again, if it's applicable, there might be some functions where it doesn't make any sense to find it, and we'll talk about that with the vertical asymptote. Step 2 is you're going to find your asymptotes. So both vertical asymptotes and horizontal asymptotes, and you've got those rules right up above on how to find those. So vertical asymptotes and horizontal asymptotes. And then for step 3, you're just going to use your calculator to sketch out what the graph looks like. Okay, so use calculator to sketch the graph. Oops, 2. So the reason we do this is that we're looking for kind of the main features of the graph, but then every graph is going to be so different. It's way different than like linear functions or quadratic functions. Every linear function is a line. They're all the same. Every quadratic function is a parabola. They're all the same. These rational functions, they have some features in common, but every single one looks completely different from the one before. Okay, so let's look at examples. Okay, so this one we've got x cubed over x minus 2. So we're going to set up our x-intercepts, y-intercepts. So your x-intercepts, remember what that means? You're going to take the numerator and set it equal to 0. So you're going to take x cubed and set it equal to 0. So really the only thing you can do with this to get x by itself, technically, you're going to be cube rooting both sides. So cube root of 0 is still 0. So that means that our x-intercept, the only one, is at x equals 0. So let's start plotting things. So x equals 0. Right there, that's our x-intercept. Okay, for your y-intercepts, remember to find where you cross this y-axis, you're going to plug in 0 for x. So plug in 0 for x, we would have 0 cubed over 0 minus 2. So 0 over negative 2, that ends up being 0. And we already knew that, because if it goes through the origin, that's also a y-intercept. Okay, next, let's talk about vertical asymptote. For a vertical asymptote, you take the denominator and set that equal to 0, because that would be where the function is undefined. And if the function is undefined, it's going to have a vertical asymptote. So all we would have to do is just add 2 to both sides, and we get the vertical asymptote. So let's plot that right here. So draw in your vertical asymptote like this at x equals 2. You sketch it in as a dotted line. Remember, that's going to be a line that your graph approaches, and it'll get really close to the farther away you get from the origin. And then finally our horizontal asymptote. So we have 3 different rules for horizontal asymptotes. If you take a look at the degrees, here you've got x cubed, so a degree of 3 versus a degree of 1. So you've got a degree of 3 in the numerator, which is greater than a degree of 1 in the denominator, and therefore, according to our rules, there is no horizontal asymptote. I still need you to write that. Even if that's the case, that you have 0 or no horizontal asymptotes, I still want you to write it, because that tells me you at least remembered to check for a horizontal asymptote, and you didn't just forget about that step completely. Okay, so we have these features drawn out. Next, we're just going to plug our function into the calculator. So of course I forgot my calculator, but this works just as well. So we're going to add a graph page. So in a new document, add a graph page, and we're going to set up a little fraction. That's a rational function. So control and then the division key. We will start with an x to the 3rd power in the numerator. And then down in the denominator, we'll have an x minus 2. So you're just typing in, right here, you type in exactly what your function is. Go ahead and hit enter and it will graph it. And so our graph looks like that. So if you look back at what we had on the page, this shape makes sense. And then it seems like there should be something on the right side. So if that's ever the case, go ahead and zoom your graph out. And we're going to do that by clicking the menu key. And you've got this whole window zoom option right here. And we are going to be zooming out. So you just center it at the origin, that's fine. And just zoom out until you see what you're supposed to be seeing. There it is. Okay, so you can see over on the right hand side here, it actually does this sort of like parabola little shape like this. All right, so we're gonna graph that function. Now notice we are way zoomed out. We're going from 70 to 80, 60 to 30. So we're gonna make a graph that makes a little bit more sense for us. But remember what it does, it kind of comes down to the right like this, looks almost like the left hand of a parabola, goes through this point, kind of wiggles back around and approaches the asymptote. So that's the left piece. And then what it does up here is it glides along the asymptote. Doesn't go all that far though before it turns around and goes back up. Okay, so it's going to look something like that. So graph your function, make sure you know how to use the calculator well enough that you'd be able to zoom in or out or get a different window on the graph, whatever you need to do to get the right picture. Okay, next example, kind of a story problem here. You've got a boat traveling upstream. We have R1 miles per hour is the speed, and then it's traveling back at R2 miles per hour. The average speed is given by this formula. Okay, so that turns into a rational function. And so we're going to start with draw the graph of R2 equals 15 miles per hour. So what we're going to do is plug in R2 equals 15. So I'm just going to rearrange this function up here. So 2 R1 and then plugging in 15 for R2 over R1 plus 15. So multiply the 2 times 15, we get 30 R1 and then over R1 plus 15. So that's the function that we're going to be graphing. Same steps that we did up above, x-intercept, y-intercept, vertical asymptote, horizontal asymptote, and then your calculator can do the rest. So x-intercept, or I guess it would be our R1 intercepts. So we set the numerator equal to 0, take 30 R1 and set that equal to 0, and then you would just divide both sides by 30 in order to get R1 by itself. So 0 divided by 30 is still 0. So start to graph your function over here. So right at 0. So these are R1 values, and then the dependent variable is capital R, according to this function right here. So our R1 intercept is right at 0. We're going to do the same thing for our y-intercept, which here is the capital R intercept. So plug in 0 for R1. So you'd have 30 times 0, and then over 0 plus 15. So the numerator is 0, the denominator is 15. That still ends up being 0, but we already had that plotted right there. So there will be times where that's not the case. That's why I'm trying to show you all these steps. Vertical asymptote. For vertical asymptote, you take the denominator and set it equal to 0 to see where the function would be undefined. Subtract 15 in order to get R1 by itself. So we end up with R1 equals negative 15. So let's plot that. Let's go ahead and scale by 5s. So 5, 10, 15. Sketch in a negative 15. So that's your vertical asymptote. That's a line that your graph will approach, but not actually cross over. And then finally our horizontal asymptote. So take a look at the degrees. This is a degree of 1. This is a degree of 1. So 1 equals 1. So that means that our, that means that our horizontal asymptote is going to be the ratio of these coefficients. So the horizontal asymptote is 30 over 1, which is 30. Okay, so let's scale this by 10. So 10, 20, 30. So that is your horizontal asymptote, is up there at 30. So remember, the way that your graph is split up, you should be expecting at least 2 pieces. So let's go take a look at our graph. So this is the one from earlier, so I'm going to clear this out. So if you hit tab and then arrow up, you can delete that. So clear it out and let's put in a new one. So another fraction, we're going to have 30, just replace the variable with x, and then x plus 15. So when we graph it, it's going to get kind of a weird picture of the graph, but you can still see we would have our vertical asymptote running right down here. Our horizontal asymptote would run right along here, and you have kind of these boomerang shapes, upper left and then lower right. So we can graph that. Okay, so we'd have a shape right in here, like that, and then another piece. Make sure you actually make it through the intercepts, like that. All right, so that's what this graph looks like. Let's quickly answer parts B and part C. What's the R-intercept of the graph? So we found this right here. R-intercept equals 0. So R equals 0 was your R-intercept, and we got that just by plugging in 0 for R1. What domain and range values are meaningful in the context of the problem? Okay, so think, context of the problem. R1 is in miles per hour. R is in average speed. You're always going forward. So like if we were just graphing the equation, this is what we'd come up with. But when we're talking about story problems, we've got context behind it. And so both of them only make sense in terms of positive values. Okay, so only positive values actually make any sense when we're talking about the context of the problems. It only makes sense that R1 would be positive. You travel upstream at positive miles per hour. You can't ever have a negative speed. And then same thing with average. It only makes sense that it would be positive. So it's really just like this little positive portion of the graph that would actually make any sense when you're talking about a story problem. Okay, that's it.